what we commonly call as artificial neural networks or deep learning networks. And what were the initial networks, and those learning techniques are utilized in modern day networks also. So as you know that neuron is the smallest processing unit in the human brain, right? So neural is derived from that word. So neural network, as the name suggests, are those networks which try to emulate the functioning of the human brain and its components, right? So because naturally the actual neural networks are those networks which are actually present in our brain, human brain. So they are the actual neural networks or the biological neural networks. And since through nodes and interconnections we are trying to emulate this behavior which is already there in our brains, since we are trying to emulate it in an artificial way, these neural networks are also known as artificial neural networks, right? So these are the information processing models that are inspired by how the biological nervous system or the brain processes the information. So as you all know that in our human brains there are neurons, right, the smallest processing unit, and then these neurons fire and trigger the neighboring neurons, and this activity keeps on going, right? On the basis of this activity, our brain has its cognition processing done, right? So for example, if we see something, on the basis of these firing of neurons, that thing is memorized in our network, in our brain, right? So our memorization is being done by firing of neurons. Then retrieval of information is again done by firing of neurons. So whatever information we perceive through our senses, eyes, ears, nose, the recognition of any smell, right? All those things are done by firing of neurons, and that information is first of all saved. So for example, if you see a rose, right? So you in your childhood must have been told by someone that if you see this type of object, it is called a flower, and this flower is called rose, right? You memorized it. It is there in your brain. So next time when you see that type of object, you immediately say, oh, okay, this is a rose. How that happens? Because your brain has been trained once upon a time, maybe whatever age you were, it was trained that, okay, this object is called a rose. So it was training object and the label. So object is what you are seeing, the image of the object, and what you are labeling is the rose, right? So first of all, your brain was trained, and then in the testing phase, you identified, okay, that this object is rose. So similarly, these artificial neural networks, these are also first of all trained, and then during the testing phase, they can recognize exactly the same information, or maybe little bit divergent information. It depends upon the robustness of the model that you have actually trained, right? So these networks are mostly used for pattern recognition, as the example I just gave you, right? The recognition of particular object or maybe pattern of information, right? So for example, you may be having 2000 data points, right? So what is the pattern in those data points? How many clusters they are forming? So that is called pattern recognition. Or maybe you trained your model to recognize some specific objects, right? Say the letters A, B, C, D, 26 characters, right? So those are the patterns that your model has learned, and then during the testing phase, you can recognize it, right? So this is pattern recognition. Data classification, right? So these neural networks are mostly used for these purposes, and till date they have obtained quite a decent accuracy of 90%. Now a few neural networks have gained even more than this, right? So they are mostly used for recognition and classification. Yes. I have just changed the slide. Can you see it? Advantages of neural networks. This is the slide. Can you see it? Okay.
No, madam.
Okay, wait.
Yes, sir. Yes, ma'am. Now we are getting.
Okay, advantages of neural networks. So whatever I was speaking till now, it was not from the slides. I was just explaining the neural network slide. So can you see advantages of neural network slide on the screen?
Yes, ma'am.
Okay. Now, see, whatever I explained till now, right, what is it showing? It is showing that neural networks can be used for identifying pattern recognition, classification in any specific domain. It depends on the type of domain on which you have shared your this thing model, right? So they can be used as experts, right? So you know, expert, like for example, there are professors with different areas of research. So suppose some professor has area of research as machine learning, right? Then he is called an expert of machine learning and he can answer queries related to machine learning. Similarly, a neural network that is trained in a particular domain. For example, you have trained a neural network in, say, market analysis, right? So it becomes an expert of market analysis. Now you can ask that model several queries, whatever comes to your mind. That okay, so tell me that what will be the price of this share, say next month. What will be the price of these shares, say next year, right? So depending on the pattern occurring in the last 10 years, your model will give you the price that may come of those particular shares which you are asking. So neural network actually solves your queries or gives response to your queries in a way as an expert will give you. And that is why they are called an expert in analyzing the category and even giving further information based on the historical data that you have trained the model. So it also answers what if questions, right? So if you have trained your model if you have trained your model on the say last 20 years data of market analysis, it can give you answers to what if question, like what if some particular mergers were there of companies, right? Or maybe some companies acquired by another company. What will be the market price then? So it can give you answers to multiple combinations. Uh, then it is this type of learning is also known as adaptive learning because it has ability to learn on the basis of the training data that you are giving or on the basis of the initial experience that you are exposing the neural network, right? These are also known as self-organizing because it creates its own organization. It constantly changes its weights and activations of the neurons on the basis of the data and information that you are giving during the training process. Uh, then it can also do real-time operations. So computations can be carried out in parallel. Then these are fault tolerant to some extent, right? So even if there is partial destruction of the neural network, so still the neural network keeps on performing, though with a little degradation. So in some cases, it can be retained even after major network damage. So even if some part of your neural network has been damaged, still you will get to some decent performance limit, you will get the results. So I have now changed the slide. Can you see the diagram on the screen?
No,
Okay. Can you see now?
yes.
Okay, just a second. I think I will share the screen. I'm trying to share the screen. The screen is not getting shared. Okay. Okay, I'm trying to share the screen. Screen is not getting shared, so I will just share this window.
Maybe, ma'am, you can rejoin. Yeah, okay. It is being shared now.
Pardon?
No, I was saying that maybe you can rejoin in case of any technical glitches. If you are going to rejoin, then it will be maybe corrected.
Okay, so another thing that I can do is I think I will not maximize this. So if it is visible in this way, is it visible?
Yes, ma'am.
So I will not maximize it. You can view it in this format. Is it fine?
Actually, ma'am, maybe updates available as showing on the PPT, and there is a cross sign. You can cross it. In the right side, top right side, you can see cross sign is there. Update now, it is some notification is there. You can cross it. Maybe it will work properly. Yeah, update now. So here in the right side, cross sign. Yeah, cross it.
No. Even if I maximize it, I change the screen, you will not be able to see the changes. Can you see application scope of neural network? I have changed the screen.
Right now it is not visible. Only the diagram is visible.
Correct. So that is
now maybe this is because of network issue. I think it is taking time to get reflected towards us.
Okay. Yes. So I am trying to share entire screen. Oh yes, I have shared the entire screen. Okay. Okay, now you can see application scope of neural networks.
Yeah, it is fine. Now fine, perfect.
Now you can see the diagram.
Yes, ma'am.
Okay, fine. Now I've shared the screen. Okay. So if you see that these neural networks find usage and application in multiple areas, like your mathematics for optimization of functions, and in approximation algorithms, then in physics for dynamical systems, statistical physics, right? For example, your annealing processes, predictive analytics in various processes. Then in engineering, they find application in image or signal processing and control theory in robotics. So, for example, you can train a neural network to analyze the motor functions. So, for example, you can have some electrodes applied on the head of any subject, any person, right, and record the EEG waves or the EEG signals. Then during that recording, you ask the person to do any motor movement, for example, right hand movement or left hand movement, and you record those signals. Then you can accordingly train the neural network to identify the patterns in these signals, to identify which signals pertain to right hand movement and which signals pertain to left hand movement, and accordingly you can pass on these signals to the robot to do the actions accordingly, right? So if a human suppose moves the right hand, the robot will also accordingly move his right hand. So for all these robotic motor movements and all these things, you can use these neural networks. Then in finance, you can use neural networks to train time series data in data mining. For example, the marketing example I just gave you. And you can use these networks for philosophy, linguistics, in natural language processing, like cognitive psychology, neurobiology, and so on. So these neural networks have a huge range of applications. For example, in air traffic control, right? So in air traffic control, you can train the neural network according to the traffic data, which can accordingly give directions to the coming planes, that which is the shortest route that they should follow. Then animal behavior, appraisal and valuation of property. So what was the trend of the prices of property in particular area? According to that, your neural network can give predictions for the coming period of time. Then betting of various types, stock markets, stock market analysis. Criminal sentencing is a very interesting usage. So for example, you can train your neural network in various laws and acts, and accordingly give the model a particular situation of a particular crime, and ask that model to give the verdict on that, right? So on what should be the verdict for a particular crime or different types of crimes on the basis of acts and laws. Then complex physical and chemical processes, normal data mining and clustering, seeing the pattern of points in a particular data set. Then direct mail advertisers. So for example, if you have a neural network, watch closely the shopping patterns of individuals, right? So for example, they can go to any Amazon or any other e-commerce website and buy certain objects. Then you can train the neural network to memorize the pattern of shopping of particular individual, and on the basis of that, you can directly send emails to that person of various advertisements and objects. So for example, if a person buys fiction books a lot on e-commerce websites, then the advertisement for different types of fiction books can be sent on emails, and similarly you can track the shopping patterns of different individuals and enhance the sales of different objects. Then echo patterns, economic modeling, employee hiring. So you can feed into the neural network the minimum requirements and the necessary qualification for different job profiles, and then feed into it the different profiles that you have obtained as a request from different people, and then the model can give you the like ranks of the individual which that model would like to choose as a prospective employee. Then you have expert consultants, like you can use your model for giving expert guidance on the market trend and share market analysis. The model can be used for fraud detection, signature recognition, character recognition, right? Even face identification, handwriting and typewriting identification, lake water levels, then machinery control, medical diagnosis. You can enter the you can train the model for different type of features or characteristics of a particular disease, and then on the basis of that have the model identify. You can do binary classification for a disease, that whether a particular disease is there or not, and you can also do multi-class classification to identify similar kind of diseases in individuals. Then music composition, photos, identification of individuals on the photos, fingerprints, recipes and chemical formulation, traffic flows, and weather predictions. So now let us see what is the individual component of a neural network. So first of all, I told you that these are an emulation of the human brain, right? And in human brain, we have neurons and interconnections between these neurons. So accordingly, the emulated behavior should also be having neurons and the interconnections. So these neurons in ANNs, or the artificial neural network, these are called the nodes, right? So they are the smallest processing elements or units in your ANN. Then these neurons or nodes are connected to each other by a connection link. Now often these connection links are having some weights. then these elements, which are the smallest processing unit, which are called the nodes, they are actually the neurons. And since this is the artificial neural network, they are also called the artificial neuron, because they have the capability to model the original or the biological neuron that is there in human brain. Internal state of neuron is also called the activation of the neuron, or the activity level of the neuron. Now, this internal state or activation is determined by the activation function that you are actually using. The neurons can send only one signal at a time. So if they are firing, they will fire, and then they will wait for some time. That is called the cooling period before they fire next. So if you see on the screen, you can see a simple diagram of a neural network having two input neurons and one output neuron. So X1 and X2 shown on the screen, they are the input neurons, and Y is the output neuron. Then these neurons are connected via interconnections which are weighted. So if you see, X1 is connected to Y with the weight W1, and X2 is connected to Y with the weight W2. So the net input is calculated. So the net input is written as YIN, right? So that is equal to X1 W1 plus X2 W2. So it is simply nothing else but the weighted sum of the input, right? You first of all weight the inputs by multiplying with the corresponding weight. So X1 into W1 is the weighted input for X1, and X2 into W2 is the weighted input for X2, and then you simply sum them all. Now this is your net input that you are actually giving to the output node Y. Now what will be the output? At the node Y, you will be applying the activation function, whatever activation function you have chosen. So that is denoted as F here. So when you apply this activation function F on net input YIN, you get the actual output, that is Y. So the function that is to be applied over the net input is called the activation function. The weight involved in ANN is equal to the slope of a linear straight line. So that is, if you know the weight, if you know the linear straight line has the equation y is equal to mx. Now this is that line which passes through the origin, right? So y is equal to mx. So this weight is actually corresponding to this m over here, which is the slope of a straight line passing through the origin. Now let us see how these artificial neural networks correspond to the biological neural networks that we have in human brain, and what are the similarities and differences between these two neural networks. So in biological neural network, we have three main parts, that is soma, dendrites, and axon. The soma or the cell body is where nucleus is located. Dendrites is where the nerve is connected to the cell body, and axon is which carries the impulses of the neuron. Okay, so electric impulse is passed between synapse and dendrites. Okay, so if you see over here, this is the schematic diagram of the biological neuron. So if you see, it is having one cell body, which is also called soma, and a long axle, which is called the axon, and then there are small nerve extensions coming out of the cell body, which are called the dendrites. Now at the tip of these dendrites, you have a small bulb-like objects. These are called the synapse. Now this electric signal actually travels from these dendrites, through these dendrites and synapse, to trigger the neighboring neuron. Okay, so these neurons are connected with each other through these dendrites and synapse. So it is actually a chemical process. So when the voltage, you can say, or electric potential of the cell body or the soma rises and crosses a particular threshold value, right? So that cell is set to fire. fire in the sense a particular electric potential, a particular electric potential travels from these dendrites and synapse to the neighboring neuron. Now, this is of particular duration and of a particular strength. Now, because of this firing of a neuron, the neighboring neuron may get excited or it may get inhibited, depending on what type of firing has been done. So, once this potential has been fired, the cell will have to wait for a particular period of time, which is called the cooling period or the refractory period. Now, in this way, each neuron actually affects its neighboring neuron, asking it to either fire itself or if it is excitatory, it will ask the neighboring neuron also to fire if its potential crosses the threshold. Otherwise, it may be inhibitory, asking the neuron not to fire and may even reduce its potential. Accordingly, you have the artificial neural network. So if you see in artificial neural network, we have input nodes x1, x2 and so on up till xn, which are weighted by weights w1, w2 and so on up till wn, which are then provided to the output neuron where their weighted sum is calculated and activation function is applied to see if this final output is crossing a particular threshold or not. If it is crossing a particular threshold, then a particular firing output is considered. That output may be 1 or any value depending on the type of activation function you are taking. Otherwise, some inhibitory value is taken. That is, it may be 0 or -1 depending on the activation function that you have taken. So you see that the net input is calculated as the weighted sum of the inputs, that is x1 w1 plus x2 w2 and so on up till xn wn, because there are n number of input nodes, right? So we will sum for all the n nodes and get a weighted sum to identify the net input. Now these synapses are said to be either inhibitory or excitatory. They are called inhibitory if they let passing impulses hinder the firing of the receiving cell, and they are called excitatory if they cause the firing of the receiving cell. So you see that these are the corresponding objects in artificial neural network for each biological neural network. That is, in biological neural network, what is called cell is called neuron in ANN. Dendrites are known as weights or interconnections. Soma, that is the cell body, is known as the net input, and axon or the main carrier of your potential is called your output. Now, these neural networks, biological neural networks and artificial neural networks, we have seen the similarities. Now let us see the differences. They differ in multiple dimensions. For example, in terms of speed, execution time is a few milliseconds in brain. However, it is a few nanoseconds in computers. So naturally, the computer networks are much faster. Processing can be done, it can be massively parallel in your biological neural network, that is human brain. However, several parallel operations can be simulated in your ANN. So, if you consider it for a small domain, right, for a particular domain, then that ANN may be faster than your biological neuron. Then size and complexity. So, human brain is naturally quite massive and the most complex neural network that can be comprehended. So it has almost 10 to the power 11 neurons and 10 to the power 15 interconnections approximately. So naturally it is more complex and difficult to understand than your computer neural networks. And in computer, the complexity actually depends on your choice, how much complex neural network you want to take and you want to design. So you can customize the complexity according to your problem that you want to solve. In terms of storage capacity, in human brain, information is stored in interconnections or in synapse strength. However, in computer, information is stored in continuous memory locations. In human brain, new information is stored without destroying the old one, right? So if you are learning new things, for example, if you are learning neural network, then whatever you have learned earlier, it won't be erased. It will be there in your brain, but new information will also occupy some part of your brain. However, if artificial neural networks, they are overloaded or they are overtrained, right? So you keep on training them with new information, then it may happen that older information may be destroyed or erased according to the storage capacity of the network. Now human brains, so this is the good thing in human brain, you keep on storing and adding new information, the old one is still there intact, and it won't be erased. But the point is there is a recalling problem. So sometimes you find it difficult to recall some information that you had stored in your brain, say 20 years back or 10 years back, right? However, this recalling problem is not there in ANN. If the information is properly stored, then it will be 100% recalled, right? And there will be no glitches. In fault tolerance, your human brain is more fault tolerant, right? So even if some problem happens, still you are able to recall most of the information. However, fault tolerance is not that up to that limit in ANN. Then storage and retrieval of information is there even if interconnections fail. However, however in artificial neural networks, if the network connections are not there or the network is disconnected, then the information becomes either corrupted or no retrieval can be there. In human brain, you can also have redundancies. However, in ANNs, there are no redundancies. In human brain, the control mechanism depends on active chemicals and neuron interconnections. In your computers, the main control mechanism is there done by the CPU or your main controlling unit. Now, these are the characteristics of artificial neural networks. So they are actually mathematical models that you are trying to emulate using nodes and interconnection model. So here we have a large number of processing elements called the neurons, and which are interconnected with each other through weights to hold the information. The input signals arrive at the processing elements through connections and connecting weights, and processing elements can learn, recall, and generalize from the given data. So computational power is determined by the collective behavior of neurons. So if you see, the information storage that is being done in artificial neural networks is not actually in the nodes, right? So information is being stored in the interconnections. That is in the form of changing weights. So as the weights keep on changing, the information keeps on getting stored. So it is the entire model that is actually holding the information rather than individual nodes. So ANNs are connection models, right? So information is stored in those connections or the weights which are actually connecting those processing units. So they are connection models, parallel distributed processing models, self-organizing systems, because the weights keep on changing as and when you keep on training the network. And then there are neurocomputing systems and neuromorphic systems. Neuromorphic systems are those which try to emulate the neurological model that is there in the human brain. So this is the evolution of neural network. They came into picture in 1943, where the first neural network was given by McCulloch and Pitts, which was also known as the McCulloch and Pitts neuron, on the name of its scientist. And here we have arrangement of neurons like a combination of logic gate, and the unique feature about these neural network is the threshold. That is the same as what we have in biological neural network. That is, if the activation level crosses the threshold, the neuron fires. So same concept is there in McCulloch-Pitts neuron also. Then in 1949 came the Hebb's network, which was again named on its scientist, that is Hebb. And here he said that if two neurons are active, then their connection strength should be increased. So this means that if one neuron keeps on firing its one particular neighbor, right, then automatically the connection between these two neurons increases. That is, the connection weight value keeps on increasing. Following this, in 1958, 59, 62, 88, and 60 came various models, including the various models of perceptron and Adeline. These were given by Frank Rosenblatt, Bloch, Minsky, and Papert, Woodrow, and Hoff. So here we have weights which are adjusted to reduce the difference between the net input to the output unit and the desired output. So this means you have some desired output, right? Now, whatever actual output you are getting, you find out the difference between the obtained output, that is the actual output, minus the desired output. This is actually called the error. Now, this error is reduced by adjusting the weight, such that in each iteration, this error keeps on reducing. Then in 1972, Kohonen gave the Kohonen self-organizing feature maps. And here these self-organizing feature maps were mostly used to cluster the data points, right, for clustering. And they are very good in clustering, that is unsupervised learning. So inputs are clustered to obtain a fired output neuron. Then in 1982, 84, 85, 86, and 87 came the Hopfield network, which was given by John Hopfield and Tang. And these are based on fixed weights and can act as associative memory networks. So associative memory networks are those networks where you have where you can store some information. That is, you can have some training data points and the corresponding labels, and you can store the points along with the labels in these memory networks, so that you can retrieve later on if you want to test. So for example, you have a photograph, right, and you have a name of that person. So say Rahul. So you have a Rahul's photograph and you have say Mohan's photograph. Now you store in those networks the photograph along with the name Rahul, the photograph along with the name Mohan. You save it, and then later on when you want to test that whether a particular person is Rahul or Mohan, you can give that photo as input to the neural network and it can identify that person. So storing the object pair relationship in a neural network is done in associative memory networks. Then in 1986 came the backpropagation network, which was given by Jumel, Hart, Hinton, and Williams. It was again a multi-layered network, and the name is backpropagation because whatever error was calculated, I told you that the difference between the actual output and the desired output is called the error, right? So this error was propagated backwards. That is, it was fed as input to the input layer neurons, so that it gets reduced in future iterations, and that is why this network is known as the backpropagation network. Then in 1988 came the counter propagation network, which was given by Grossberg, and this was quite similar to the Kohonen network. Then in 1987 to 90 came the adaptive resonance theory, that was given by Carpenter and Grossberg, and it was designed for binary and analog inputs. Then in 1988 came the radial basis function network given by Broomhead and Louis. So this resembles back propagation network, but activation function used is your Gaussian function. Then in 1988 came the new cognitron that was given by Fukushima, and it was mostly used for character recognition. So basic model of artificial neural network is based on three entities. First is your synaptic interconnections. That is your how your neurons are interconnected and how those weights are changing. Then training or learning rules adopted for updating and adjusting the connection weights and their activation function. So activation function is actually responsible to identify the activation state of a particular neuron, right? So activation function is important when you want to identify the activation state. The arrangement of neurons to form layers and the connection pattern formed within and between layers is called the network architecture. So network architecture actually means how many neurons you are having in the input layer, how many neurons you are having in the output layer, and whether you have any hidden layer or not, and what are the weights of these interconnections. So you have 5 different types of neural networks. One is your single layer feed forward network, then multi-layer feed forward network, then single node with its own feedback, single layer recurrent network, and multi-layer recurrent network. So what you see on the screen is a single layer feed forward network. So this layer is formed by taking processing elements and combining it with other processing elements. So input and output are linked with each other. Now, because it is a single layer, right, you will just have one input layer. That's all. Okay, so only the input layer. Input is, so if you see the layer that you can see on the screen is your input layer. And here inputs are provided to each neuron, and the final outputs are taken. So inputs are connected to the processing nodes with various weights, and this results in the series of outputs, one per node. So it depends on how many output node you are having. You may have one node, so you will get one output. Otherwise, you can have a number of nodes in the output layer. Now, always remember when you are designing a neural network, the number of classes that you have to classify. So many nodes you take in the output layer. So, for example, if you are doing binary classification is you want to test whether a particular a particular individual is having flu or not, right? So it is a binary classification, that is 1 or 0. If a person is having flu, the output value is 1. If a person is not having flu, the output value is 0. So this is called binary classification, yes or no, having flu or not having flu. Okay, so in that case, you will have just one neuron in the output layer. Otherwise, if you have 2 classes, you take 2 neurons in the output layer, 3 classes, then you take 3 neurons in the output layer, and so on and so forth. Now, what you see on the screen is a multi-layer feed-forward network. So multi-layer feed-forward means one input layer will be there, one output layer will be there, and then a number of hidden layers can be there. Say n number of hidden layers can be there. So this is formed by the interconnection of several layers. So input layer is there to receive the input and it buffers the input signal. And from the output layer, you can get the output. Always remember that for any type of neural network, the number of neurons in the output layer is equal to the number of classes that you want to classify. Okay. But the number of input neurons is always there according to the number of features that you have in the input data. Suppose you are having n number of features in the input data, then you will be having n number of nodes in the input layer. But you can have any number of nodes in the hidden layer that you can decide on the basis of the domain whose problem you are solving. So this hidden layer is internal to the network. 0 to multiple hidden layers can be there in the network. There is no upper limit on the number of hidden layers that you can have. However, you are bounded by your resources, right? So if you keep on increasing the number of hidden layers, your neural network will take a lot of time to compute the final result, and therefore you are bound by the resources. If your resources allow you to keep multiple hidden layers, you can keep them. But more the hidden layers, that is, if you keep on increasing the number of hidden layers, the complexity of the network keeps on increasing. But as you increase the number of hidden layers, the output or the performance also increases. So this is kind of trade-off between the complexity and performance, right? That you have to take a decision when you are solving a problem. Then we have the feedback network. So if no neuron in the output layer is an input to a node in the same layer or the preceding layer, it is a feed-forward network, right? This means there are no self loops formed. Then it is a feed-forward network. However, if the inputs are directed back, if the outputs are directed back as input to the processing elements in the same layer or the preceding layer, it is also called a feedback network. So if the output is directed back to the input of the same layer, then it is called a lateral feedback. Recurrent networks are those networks which have feedback networks with closed loop. So if you see on the screen, you have figure 2.8a. It shows a simple recurrent network having a single neuron with neural feedback to itself, right? And since it is having a feedback, it is also called a recurrent network. Since it is the feedback neural network with one node, it is called a simple recurrent network. In figure 2.9, you see it is a single layer network with feedback from output that can be directed to the processing element itself or to other processing elements or both. So if you see on the screen, there is there are output nodes y1, y2, y3 and so on. So the output has been taken as input back to y1 and also to y2, y3 and so on until yn. Okay, so this is again a feedback network, that is a recurrent network. Now the figure that is labeled as B, these are called the max net or the competitive nets. So in these are called the competitive nets. Why? Because only one node can be on at a particular moment of time. All the other nodes are off. If you see that interconnections are having negative weights, so minus epsilon is being shown as the weight, because at any point of time only one node is on. That means having value 1, activation value 1, others are having activation value 0. Then another type of network is on center off surround or lateral inhibition structure. So each processing neuron receives two different classes of inputs, excitatory and inhibitory. So excitatory input is from the nearby processing element, and inhibitory elements you get from more distantly located processing elements. Then processing element output can be directed back to the nodes in the preceding layer, forming a multi-layer recurrent network. So if you see on the screen, the network that you can see is a multi-layer recurrent network because it is having one input layer, which is x1, x2 and so on up till xn. It is having one output layer, that is y1, y2 and so on up till ym. And it is having one hidden layer also. Since it is having, if you have any layer other than input and output, then your network becomes multi-layer. Okay, so this because of this hidden layer, it is now being called as the multi-layer recurrent network, because your output is coming back as a lateral feedback to the hidden layer z1, z2, z3 and so on. Right, so this is a multi-layer recurrent network. So processing element output can be directed to processing element itself or to other processing elements in the same layer. So there are two broad kinds of learnings in artificial neural network. One is your parameter learning, another is structure learning. So in parameter learning, you are actually updating the weights of the interconnections. But in structure learning, you want to change the entire architecture or the structure of the network. So apart from these, learnings in ANN can be classified into 3 different types. One is supervised learning, another is unsupervised learning, and third one is reinforcement learning. So let us see quickly brief definitions of each one of them. So when you learn with the help of a teacher, right? So you are a child, in your childhood days, you went to schools, right? And you didn't know anything, absolutely nothing. And the teachers were there in your class. They used to tell that if you draw this image on the board or on the paper, it is called A. If you draw this image, it is called B, and so on. So what is happening? You are being taught, and you are being your brain is trying to identify some patterns, some objects, and the labels are also being provided to you by your teacher. So this type of learning is called supervised learning because you are learning object and their label under the supervision of your teacher. Similarly, in artificial neural network, for each input vector, you have a target vector, right? So you have actually input target pair, which you provide to your neural network. Now, this target vector is actually your desired output. The input vector along with target vector is actually called the training pair. So you provide, during the training process, you actually provide this pair, that is the input and the desired vector pair. But you provide the input vector and some output you get. So this is called the actual output. Now this actual output is then compared with your desired or the target output. If there is a difference, then this is an error, and the corresponding error is generated, which is then fed back again to the neural network so that this error can be reduced. And weights are adjusted accordingly so as to reduce this error. In unsupervised learning, so for example, a tadpole learns to swim by itself, right? So it may be possible that there may be few people who don't go to school, but for example, you suppose even when you have not gone to any school, you learn to speak many things in whatever your native language is. Suppose if your native language is Hindi, even when you don't know how to read or write Hindi, you will be able to speak Hindi, right? How that has happened? That has happened by self learning. You heard some things, you understood, and then you learned that okay, so this word means this, right? So even without supervision, you learn your native language, your mother language, even without going to school. So this is an example of unsupervised learning. That is, in unsupervised learning, nothing is given to you, label is not given to you. You just see the patterns and you identify the patterns. So in ANN, during unsupervised learning, the network just receives the input pattern and organizes it to form clusters. So if you see from this figure, it is observed that no feedback is applied from the environment to inform what output should be or whether they are correct. You are only identifying some patterns in the provided input. Okay, so this type of learning is called unsupervised learning. The neural networks can self-organize themselves or can self-adjust their weights, and therefore in unsupervised learning, the neural networks are also known as the self-organizing networks. Then third type of learning is your reinforcement learning. Now in reinforcement learning, suppose you don't have a teacher, you don't have a very kind teacher who tells you what you have to who tells you the actual answer to some particular problem. You have a critical teacher who just criticizes you, gives you award and gives you punishment. So for example, if you identify A correctly, then you are awarded with some incentive. Otherwise, if you identify it incorrectly, you are punished with some, say, minus marks. right? So this type of learning is called reinforcement learning. So what happens is some data is given to the neural network, and then on the basis of the decision, the final prediction that the neural network is doing, the neural network is either given an award or a punishment, you can say, on the basis of the steps that it is taking. So this reinforcement type learning is quite helpful in robotic movement. Okay, so here's some environmental feedback you get from the environment, that whether the action that was taken was correct or incorrect. Accordingly, the weights are adjusted and error is reduced in each iteration. Now let us see the activation functions, which are an important part of your neural network. So to make work more efficient and for exact output, some force or activation is given. There's also kind of incentive, right, where you are trying to, identify the actual value of the net input that you have got and see if it is greater than or less than a particular threshold value that you have chosen. So activation function is applied over the net input to calculate the output of a particular ANN. So information processing element has two major parts, input and output. So an integration function is associated with the input of the processing element. So we can have several different types of activation functions. The most simple one is your identity function. Now, this identity function is mostly applied at the input layer, right? So here, identity function simply means you simply replicate the values. That is, fx is equal to x. So this is a linear function having simply y is equal to x. That is, fx is equal to x. So output is exactly the same as the input. So this identity function is applied at the input layer where you are applying the inputs. Then another activation function is your binary step function. So it is defined as 1 if x is greater than equal to theta, and 0 if x is less than theta, right? So here the values of fx are either 1 or 0, and that is why it is a binary step function. Theta here is your threshold. So it is used in single layer networks to convert the net input to the output. So whatever is your net input, your final output is only 0 or 1. Then similarly, you have the bipolar step function. So in bipolar, your values go from 1 and minus 1, not 0. So fx is 1 if x is greater than equal to theta, and fx is minus 1 if x is less than theta. So theta represents the threshold value, and the output ranges from plus 1 to minus 1. Another is your sigmoid function. This function is mostly used in backpropagation networks. So this is again of two types, binary and bipolar. So in binary sigmoid function, you have your equation as fx is equal to 1 upon 1 plus e to the power minus lambda x, where lambda is your steepness parameter. So this, if you find out the derivative of this function, that is f dash x, this is equal to lambda fx 1 minus fx. So the range of the sigmoid function is again 0 to 1. Hence it is binary sigmoid. Another type of sigmoid is bipolar sigmoid, which is given by equation 1 minus e to the power minus lambda x upon 1 plus e to the power minus lambda x, where lambda is your steepness parameter and the sigmoid range is between minus 1 and plus 1. So the derivative of this function is lambda by 2, 1 plus fx and 1 minus fx. So it is closely related to hyperbolic tangent function, written as 1 minus e to the power minus 2x upon 1 plus e to the power minus 2x. So derivative of this hyperbolic tangent function is h dash x, that is 1 plus hx and into 1 minus hx. Then finally you have your ramp function, where fx is equal to 1 if x is greater than 1, and x if x ranges from 0 to 1, and it is 0 if x is less than 0. So you can see the graphical representations of these functions in this figure. So your figure A shows the identity function naturally. Y is equal to x is a straight line passing through the origin with slope is equal to 1. Then the image B shows the binary step function, that is fx is equal to 1 if x is greater than equal to 1. So here your theta is 1, okay, and it is 0 if x is less than 0. Then in C you have the bipolar step function, that is fx is equal to 1 if x is greater than equal to 1, and it is 0 if it is between -1 and 1, and if it is -1 if it is less than -1. In D, you see D and E. Actually, you see the sigmoidal function. So D, you see the binary sigmoidal function, and in E, you can see the bipolar sigmoidal function. In F, you have the ramp function, that is fx is equal to 1, which is this one. Fx is equal to 1 if x is greater than 1. Otherwise, if x is between 0 and 1, it is x. And if x is less than 0, it is 0. Now let us see the important terminologies of ANNs. One is your weight. So weight contains information about the input signal. It is used by the net to solve the problem. Even if you want to store information, for example, associative memory networks, there the information is stored in the form of weights only. So these weights are represented in terms of matrix and are also known as connection matrix. So if this weight matrix W contains all the elements of an ANN, then the set of all weight matrices W will determine the set of all possible information processing configurations. So the ANN can be realized by finding an appropriate weight matrix W. So weights encode long-term memory, and activation states of network encode short-term memory. Right. So when I say long-term memory, it actually means the weights or the interconnections, and the short-term memory actually means the activation states of the neurons in a neural network. The bias is actually a small parameter that you see as B written over here in the equation B. So this bias is actually used to shift the you can say classification boundary. Okay, so when just shifting the classification boundary can give you a better classification, you use the bias. So bias has an impact in calculating the net input. So it is included by adding x naught to the input vector x, and the net input is calculated by yin j is equal to bj plus summation I is equal to 0 to n xi wij. So the bias is of two types, positive bias and negative bias. So positive bias is used to shift the classification boundary towards the right or towards the positive quadrant, and a negative bias is used to shift the classification boundary towards the left, that is towards negative quadrant. So positive bias increases the net input and negative bias decreases the net input. Another one is your threshold. It is a set value based upon which the final output is calculated. So calculated net input and threshold is compared to get the network output. So the activation function of threshold is defined as 1 if the activation function is greater than equal to theta, and -1 if it is less than theta. So here theta is the fixed threshold value. Another is your learning rate. So this is denoted by alpha. So learning rate should be kept optimal. If it is generally kept in the range of 0 to 1. But if it is close to 1, then your network will be reaching convergence very quickly, and therefore you may miss the global optima. You may land into a local optima. But if it is too close to zero, then your network will be converging very slowly. So it will take many iterations to come to the final optimal value. So you should take an optimal value of alpha such that it is neither too very high nor very low. Then you have momentum factor. So convergence is made faster if a momentum factor is added to the weight updation process. So this is actually done in back propagation network. Then you have the vigilance parameter denoted by rho. So it is used in adaptive resonance theory network. So it is used to control the degree of similarity. So it ranges from 0.7 to 1 to perform useful work in controlling the number of clusters. Now let us see the first neuron that came into picture in 1943, given by McCulloch and Pitts, and was named after its scientist, that is McCulloch-Pitts neuron, also known as the MP neuron. So this MP neuron are connected by directed weighted paths. So activation of MP neuron is binary, that at any time step the neuron may fire or may not fire. So the weights associated with communication links may be excitatory, that is weights are either positive, or inhibitory, that is the weights are negative. So threshold plays a major role here. There is a fixed threshold for each neuron, and if the net input to the neuron is greater than the threshold, then the neuron fires. So they are widely used in the logic function. So when you want to emulate logic function and or NOT gates, you mostly use the McCulloch-Pitts neuron. So a simple MP neuron is shown on the screen. So here you see that it is having two types of weights, W and P. So if the weight is excitatory, then it is W. So W is greater than 0. And if it is inhibitory, the weight is P. So P is less than 0. So in this figure, inputs from X1 to Xn, they possess excitatory weight connection, and from Xn plus 1 to Xn plus M, you have inhibitory weighted interconnections. So since the firing of neuron is based on threshold, activation function is defined as 1 if net input is greater than equal to theta, and is 0 if net input is less than theta. So you see that this is a binary activation function. So for inhibition to be absolute, the threshold with the activation function should satisfy this inequality, that is theta is greater than NW minus P. Then only the activation, then only it will be inhibition. Otherwise, the output will fire if it receives K or more excitatory inputs, but no inhibitory input. So that means theta is just less than equal to Kw and is greater than K minus 1 into W. So the MP neuron has no particular training algorithm. It is just based on this theory. And analysis is performed to determine the weights and the threshold. So it is mostly used as a building block for the logic functions and gates. Then there is the concept of linear separability. So it is a concept wherein the separation of input space into regions is based on whether the network response is positive or negative. So this linear separability concept is there only for those data points which are actually linearly separable. That is, they lie in space such that a single straight line can be used to separate those two regions where these data points are lying. So the decision line is also called as decision making line or decision support line and linear separable line. So the net input calculation to the output is given as yin is equal to bj plus summation I is equal to 1 to n xi wi. So the region which is called as the decision boundary is determined by the relation b plus summation I is equal to 1 to n xi wi is equal to 0. So that means when net input is equal to 0, and this equation becomes 0, that is actually the decision boundary. So this is the equation of the decision boundary. So you consider a network having positive response in the first quadrant and negative response in all other quadrants with either binary or bipolar data. So if you draw a decision line separating these two regions, this is your linear separable line. So using bipolar data representation, you mostly use a bipolar data representation because in this you can represent the missing and unknown data, missing or and mistaken data in a different way. So if your data is missing, then it is represented by 0 and mistakes are represented by just reversing the sign. So +1 is represented by -1 and -1 is represented by +1 if you want to indicate a mistake, and if you want to indicate a missing value, you just write a 0. Then next came the Hebb network. So Donald Hebb stated in 1949 that in brain, the learning is performed by the change in the synaptic gap. So when an axon of cell A is near enough to excite cell B and repeatedly or permanently takes place in firing it, some growth process or metabolic change takes place in one or both the cells such that A's efficiency as one of the cells firing B is increased. Okay, so this means that if cell A, suppose any cell A is constantly firing another cell B, then the weight interconnection between these two cells should increase because they have some greater interconnection, some greater connectivity such that one cell A is constantly firing cell B. So this weight vector, so this means that if there are two cells A and B which are interconnected, the weight vector which represents this interconnection is found to increase proportionately to the product of the input and the learning signal. So in Hebb learning, two interconnected neurons are on simultaneously. So the weight update in Hebb is given by Wi new is equal to Wi old plus Xi y. So it is suited more for bipolar data. So if binary data is used, the weight updation formula cannot distinguish two conditions. So if you are using a bipolar data, that is only 1 and 0 values, then you have X into Y. You will not be able to identify which of these parameters is 0. That means a training pair in which an input unit is on and the target value is off, right? So this means that X is 1 and Y is 0. Or the training pair in which both the input unit and target value is off. That means X is also 0 and Y is also 0. You can't distinguish between the two because the product is 0 in both the cases. So this is the flow chart of training algorithm. So first you initialize the weights, then you perform steps 2 to 4 for each input training vector and the target output pair. So here the input training vector is represented as S and the target output pair is represented as T. So you have S colon T. So input activations are set. The activation function for input layer is identity function. So xi is equal to si for I is equal to 1 to n. And output activations are set y is equal to t. So this means you provide the input at the input layer and you provide output at the output layer. And then you do the weight adjustment and the bias adjustment in step 4. So wi new is equal to wi old plus xi y and b new is equal to b old plus y. So here we are just writing y because there is only one output node, right? So no subscript for y, only one output node is there. Then in step 4, the weight updation formula can be written in vector form as w new is equal to w old plus xy, where x is your vector and w old and w new is also a vector. Then change in weight is expressed as delta w, that is equal to xy, right? So w new is equal to w old plus delta w. So Heb rule is used for pattern association, pattern categorization, and pattern classification over a multiple range of areas. So that will be all. So let us meet now again at 6. Okay, after you can say half an hour approximately. Okay, see you all again at 6.
Okay, ma'am. Thank you.
Okay, thank you all. Hello everyone, welcome back. I'll be now sharing the slides. So we will be now starting with the perceptron. I hope the slides are visible. Are the slides visible?
Yes, ma'am, it is visible.
Okay, thank you. So let us now start with the perceptron networks. These are typically, we'll be mostly covering the supervised learning networks. So as I have already discussed, the three types of learning categories: supervised, unsupervised, and reinforcement. So we will be first of all covering the supervised learning networks. So here we have a and training and labeled paired set which we provide to the network. So in the training set we have input and target values, and that we provide to the network, and so that it gets trained on the particular set of values. Now, the simplest form of neural network is a one neuron neural network, right? So, if you have just one neuron acting both as the input layer and the output layer, it is called a perceptron. Now, this perceptron, as you can see on the screen, there is one single node that computes the weighted average, that computes the weighted sum of all the inputs, and then applies the activation function to find out the final output. So this perceptron has one neuron that does this operation of finding the weighted sum of the inputs, and then applying the activation function to see if the net input is greater than a particular threshold value. If it is greater than the threshold, then the final output is 1, and if it is less than the threshold value, then in case of bipolar network, the output is -1. These perceptrons are also known as linear threshold unit. Why? Because a single neuron perceptron can only be used to classify linearly separable data. I already told you what a linearly separable data is. So when linear separability is there, then only a single neuron perceptron can be used. Single neuron perceptron architecture will look like the image that is shown on the screen. So here you have n number of inputs with weights, corresponding weights, W1, W2, and so on up till Wn. W0 is your bias. Now this is applied over the neuron, and a weighted sum is calculated. So summation I is equal to 0 to n Wi xi. Then activation function is applied on this net input, and the final output effects is 1 if this summation is greater than 0, otherwise it is -1. So let us see the perceptron learning. So Wi is equal to Wi plus delta Wi. So this is delta Wi is the change in weight. So that is equal to eta t minus O xi. So eta is your learning rate, that is a small constant ranging from 0 to 1. T is the target value, that is the target label that you have trained your network on, and O is the perceptron output, the actual output that is being provided by the network. If the output is correct, that is T is equal to O, then the weights Wi are not changed. Naturally, if T is equal to O, delta Wi will become 0, and since it is 0, Wi new will be equal to Wi old. So weights will not change. If the output is incorrect, that is T is not equal to O, the weights Wi are changed such that the output of the perceptron for the new weights is closer to T. That means this error T minus O has to be reduced. The algorithm converges to the correct classification if the training data is linearly separable. So for all eta which is sufficiently small. So this means perceptron learning is only suitable for linearly separable data. Now what is epoch? So if you have presented the entire range of training data set to your neural network, then it completes one iteration and hence is called one epoch, right? So presenting the entire training set to the neural network is one epoch. So in the case of the AND function, an epoch consists of 4 sets of inputs being presented to the network, right? So 0, 0, 0, 1, 1, 0, 1, 1. So this means when you present all these 4 pairs to the neural network, then it will complete one epoch or one iteration. Then error is the value with which the target value differs from the obtained value. That is the amount by which the value output by the network differs from the target value. So for example, if we require the network to output 0 and it outputs 1, then the error is minus 1. That is desired output minus actual output. So the error is desired output minus actual output. So when we are training a network, we not only present it with the input, but also with a value that we require the network to produce. So that is actually your label. So for example, if we present the network with 1, 1 for the AND function, the training value is 1 and the target value is also 1 here. So this is the actual target value, right? And output is the output that is being given to the neural. Can you please mute your mic? Some noise is coming. Okay. So ij is the inputs being presented to the neuron, and wj is the weight from the input neuron to the output neuron. LR is the learning rate. So this dictates how quickly the network converges. So any value you can choose, and later on you can run your iterations with different learning rates so as to just check that you don't skip the global optimal value. So generally, typically, what people take is 0.1, but you can test with different values also. Now let us see the training algorithm of perceptron. So you adjust the neural network weights to map the inputs to the outputs. So in training process, what is actually done is the adjustment of the weights. So you use a set of sample patterns where the desired output is known. So you take some sample patterns along with the target value. So the purpose is to learn to recognize features which are common to good and bad exemplars. Right. So this means so that whatever, suppose you are having binary classification, yes, no. So you should be having approximately equal number of instances pertaining to both the classes. If you suppose you want to check whether a person is having flu or not based on some symptoms. Now those symptoms are actually your features of the data set, right? Yes, value yes means the person is having flu, so that is your one class. Value no, that means the person is not having flu, is your another class. Now some rows will be pertaining to value yes and some rows will be pertaining to value no. So these rows are actually instances of class yes and class no. Now these two instances should be approximately equal. So suppose in a data set of 100, you have 50 instances of yes and 50 instances of no. Then this situation is called a balanced data set. You should always prefer to take a balanced data set, right? It should not be the case that for yes class you are having 10 instances and for no class you are having 90 instances. If that is the case, your data set will be called as imbalanced And what will happen is it will only train the model according to the no class, and very less training will happen for the yes class. So as a result, it will accurately classify the instances of no class, but will not be able to properly classify the instances of yes class. So you should avoid this type of situation and try mostly to take a balanced data set. Now let us see the perceptron training algorithm for single output class. Now let us see that case where we just have one single output class, that is only one neuron in the output. So the perceptron algorithm can be used for either binary or bipolar input vectors having bipolar targets. So threshold can be fixed and bias can be variable. So this algorithm is not sensitive to initial values of weights or learning rates. So you can initially take any value for the weight, and they can also be set to 0. So let's see the algorithm. In step 0, you initialize the weights and the bias. They can also be set to 0. Then you initialize the learning rate. That can be any value from 0 to 1. Then you perform steps 2 to 6 till the stopping condition becomes true. And then you perform steps 3 to 5 for each training pair indicated by S and T. So the input layer containing inputs is applied with identity activation function. So you simply apply your inputs to the input layer, that is xi is equal to si, right? Because it is identity activation function, right? So y is equal to x. Then you calculate the output of the network. First calculate the net input, that is yin is equal to b plus summation I is equal to 1 to n xi wi, and we know that b is the bias, x is the input, w is the weight. So when n is the number of input neurons, then you apply the activation over the net input to obtain the output. So when you apply the activation function over this net input yin, it is equal to 1 if yin is greater than theta, 0 if yin is between minus theta to theta, and minus 1 if yin is less than minus theta. Then finally, as a final step, the weight and bias adjustments are done. You compare the value of the actual output and the desired output. If this value is not equal, that is y is not equal to t, then wi new is equal to wi old plus alpha t minus o xi, where t is your target value, o is the actual output that you have got, alpha is your learning rate, and xi is the input provided at the ith neuron. B new is your new bias, that is equal to B old plus alpha t minus O. So otherwise, if y is equal to t, right, that means that there is no error. The target value is equal to the obtained value. In that case, no change in weight and no change in bias. Wi new is equal to Wi old, and B new is also equal to B old. Then you train the network until there is no weight change. And if this condition is not met, then again you can start from step 2. So this was your training algorithm for single output class neuron, perceptron. Now suppose for multiple output classes are there, right? Now this is for multi-class classification. So here you initialize the weights, biases and learning rates suitably. Or you can take any random values initially, because whatever values initially you take, they do not affect the final result. Then you perform steps 2 to 6 till stopping condition becomes true. And then in step 2, you perform steps 3 to 5 for each training pair indicated by S:T. So S:T simply means S is your input vector and T is your output vector. That is desired or the target output vector. So the input layer containing inputs is applied with your identity activation function, right? So you simply apply your input vector values to your input layer neurons. And then you calculate the output response of each output unit. J is equal to 1 to m. So you first calculate the net input yin, that is equal to bj plus summation I is equal to 1 to n xi w ij. This Wij is the weight between the ith input neuron to the jth output neuron. Yinj is the net input at the jth output neuron. Then you apply the activation over the net input to obtain the output. So after applying the activation, you get Yj, that is the final output at the jth output neuron, that is equal to 1. If net input is greater than theta, that is Yinj is greater than theta. It is 0 if net input lies between minus theta and theta, and this is -1 if net input is less than minus theta. Then you make adjustments in weights and bias for j is equal to 1 to m and I is equal to 1 to n, right? So this means that number of output nodes is m, number of input nodes is n. Now, if your target output value is not equal to actual output, that is Tj is not equal to Yj, then you change the weight and you change the bias. So Wij new is equal to Wij old plus alpha Tj xi, and Bj new is equal to Bj old plus alpha Tj. So else we have no change in weight and no change in bias. Wij new is equal to Wij old and Bj new is equal to Bj old. Then finally you test for the stopping condition, that is if there is no change in weights, then stop the training process, else start again from step 2. So in figure 3.2 you see a single classification perceptron network. That means you have a single output node. This type of perceptron network is used for binary classification. I told you then that when you have to do just binary classification, you take only one neuron in the output layer, because the output value of that neuron can be either yes or no, 1 or 0, right? So it is simply binary classification. When you have to do multi-class classification, the number of neurons in the output layer is equal to number of classes that you want to classify. So in figure 3.4 you see that the number of neurons in the output layer is m, right? Y1, Y2, Y3 and so on up till Ym. So this means the number of classes that you want to classify is m. And you have n number of neurons in the input layer. So this means n features are there in the input data set, right? And therefore for each feature you have to take one neuron in the input layer. And since it is a perceptron, in perceptron we don't have hidden layers, right? Only the input and the output layer. So let us see the testing algorithm for perceptron. So the initial weights are taken from the training algorithm. So whatever final weights you have obtained after completing the training process, right? Those weights are taken here for the network. So the weights are initialized as the weights which you actually obtained after the training process. Then for each input vector X to be classified, you perform steps 2 to 3. Set activations of the input unit. That is, you simply apply the testing vector over the input layer of the perceptron, and then you obtain the response of the output unit. So Yin is equal to summation I is equal to 1 to n xi wi. So then after this you will simply apply the activation function over this net input, right? So that is equal to 1 if net input is greater than theta. It is 0 if net input lies between minus theta and theta, and it is -1 if net input is less than minus theta. Now, in multi-layer perceptron, you have input layer where the input signal is provided. Then you have the adjustable weights and you have the output layers. Now, we have three types of layers in neural network: input layer, output layer, and hidden layer. So this input layer introduces input values into the network, and no activation function or other processing is done here, because in most of the neurons, in most of the neural networks, if you see, the activation function that is used at the input layer is identity activation function, right? Which is actually no function is being applied. Y is equal to X, right? Now at the hidden layer, this actually does the classification task, right? So this performs classification of the features. Generally, 2 hidden layers are sufficient to solve even a complicated problem, and more the features imply more number of layers. So more the features, more the layers, and therefore we call it a curse of dimensionality, right? Because dimensionality means dimensions. That means if you have, say, k number of features, right? If this k is small, say 5, so this means you are having only 5 features, 5 columns, right? This is a small number. This is quite handleable, right? So it will not create any problem. But suppose this k is 1000. So that means you have 1000 columns in your entire data set. Now this is not quite manageable. This means a very high dimensionality you are having, high number of features you are having, and to handle this high number of features, you can do 2 things. Either you reduce the number of features, which is called feature selection. That means you will just take important features by applying some feature selection technique, and you leave out the remaining features, right? So by that you are actually reducing the dimensionality, and hence less number of neurons will be required in the input layer. Suppose you reduce your 1000 features to say 100 features. So now only 100 neurons will be required in the input layer. But suppose you don't use any feature selection method, then you will have to use 1000 neurons in the input layer, which will take a lot of time to compute, right? So, and that is why more the features, more the complication involved in your neural network. Then you have the final output layer, whose functionality is also just like the hidden layer. But here you get the actual output. That is the actual classification task is being done by the output layer. Another type of neural network is your adaptive linear neuron, popularly known as the Adeline. So in 1959, Bernard Bidrow and Marcian Hoff of Stanford, they developed models which they called as Adeline, that is adaptive linear neuron, and Madeline, multi-layer adaptive linear neuron. So these models were named for their use of multiple adaptive linear elements. So Madeline was the first neural network to be applied to a real world problems. Actually, Adeline and Madeline, they both were developed to filter the noise that actually comes in the telephone lines. So for signal processing, these two neural networks were used. Adeline or the adaptive linear neuron was not that efficient, and therefore multiple Adelines were combined together to get a better output, which came to be known as the multi-layer Adelines or the Madeline network. So a network with single linear unit is called an Adeline or adaptive linear neuron. So in an Adeline, the input-output relationship is linear. So just like your perceptron, Adeline can also be used where the data is linearly separable because you have a linear input-output relationship. Adeline uses bipolar activation for its input signals and its target output. So the weights between the input and the output are adjustable, just like your perceptron. The bias in Adeline acts like an adjustable weight, so your bias is also adjustable. And it is a net which has only one output unit. So Adeline network can be trained using the delta rule. So this delta rule is also known as the least mean square rule or the Wittrow-Hoff rule. So this rule is based on minimizing the error, that is MSE, mean squared error between the activation and the target value. Now let us see the delta rule. Now delta rule is quite similar to the perceptron learning rule, but their origins are a little bit different. Perceptron learning rule originates from the Hebbian assumption, while the delta rule is derived from the gradient descent method. So the perceptron learning rule, you remember perceptron learning rule, we have alpha t minus ox, right? That was delta w. So that is the learning rule. Whatever is the change in weight, that is the learning rule, that is alpha t minus ox. So this perceptron learning rule stops after a finite number of learning steps. But the gradient descent approach continues forever, converging only asymptotically to the solution. That is, it converges very slowly after each iteration. So the delta rule updates the weights between the connections so as to minimize the difference between the net input to the output unit and the target value. So your ultimate goal in both delta rule as well as perceptron is to minimize this error. That is the difference between the target and the actual output. So the major aim is to minimize this error, that is T minus O, over all training patterns. So this is done by reducing the error for each pattern one at a time. So the delta rule for adjusting the weight of the ith pattern is equal to delta Wi is equal to alpha T minus Yin Xi. So that is for single output, and delta Wij is equal to alpha Tj minus Yinj Xi for several output units. This is the architecture of the headline model that you can see. So here we have n inputs, right? So x1, x2, x3, and so on up till xn. Then we have their corresponding weights, w1, w2, and so on up till wn. And b is the bias. So first of all, we calculate the net input, that is yin, that is summation of the weighted input, that is xi wi, and then you apply the activation function. So before applying the activation function, you find out the error. What is the difference between this obtained obtained output and the target output? So this E is equal to T minus Yin, and then you adapt this the weights of the network such that this error is reduced in the next iteration. So this Adeline learning rule, in Adeline network, it uses the delta learning rule. So this rule is also called as the Whitrow-Hoff learning rule or the least mean square rule. The delta rule for adjusting the weights is given as delta Wi is equal to alpha T minus Yin into Xi. So delta Wi is equal to weight change. So the delta W is the change of weight that is done in each iteration. Alpha is the learning rate. T is the target output. Yin is the net input to output unit, right? And X is the vector of activation of the input unit. So you see the basic difference between Adeline learning rule and perceptron learning rule. In perceptron learning rule, you were calculating T minus O, that was the actual output. And here you are calculating T minus net input. So let us see the training algorithm for Adeline. The weights and bias are set to some random values, but not zero. So then you set the learning rate parameter alpha. So you perform steps 2 to 6 till stopping condition becomes true. And then you perform steps 3 to 5 for each training pair indicated by S and S:T. So the input layer containing inputs is applied with identity activation function. You simply apply the input vector over the input layer neurons, right? And then you calculate the net input to the output unit. So Yin, this is equal to B plus summation I is equal to 1 to N Xi Wi. So where N is the number of input neurons. Then you update the weights and bias for I is equal to 1 to N. So Wi new is equal to Wi old plus alpha T minus Yin Xi, and B new is equal to B old plus alpha T minus Yin. If the highest weight change that occurred during training is smaller than a specified tolerance, then you stop the training process, else continue. Right? So suppose that delta W becomes very small, right? No significant change is happening. You can take small, means some threshold value you can take, epsilon. When delta W becomes less than epsilon, right? At that point you can stop. So this is the test for stopping condition of the network. This is the flow chart for the Adeline training process. So So again, the same thing, you set some initial weights for the for all the W's and the learning rate alpha, and then you have some threshold tolerance error, say E, S or epsilon. Then you apply all the input vector on the input layer neuron, and you calculate the net input, that is B plus summation xi wi, and you apply the activation function. So before applying activation, you find out the error, that is alpha t minus yn xi, that is delta w also. Now, if this delta w is less than, this error is less than your threshold, that is epsilon or es, then you stop. Otherwise, you continue this iteration. So it comprises three main steps of initialization, training, and thinking. So in initialization, you assign some random weights and bias to all the links. In training, you feed in known input in random sequence and you simulate the network. So feeding the input, the sequence in which you feed the inputs to the network, it really doesn't matter. So in any sequence, you can feed the instances into the neural network. Then you compute the error between the input and the output, that is T minus yin, and then you adjust the weights, that is the learning function, and you repeat this process until total error is less than some epsilon value. And thinking comprises simulating the network. This is actually mainly the testing process, that is, you simulate the network and you give any random input to the network to which the network will respond. However, it does not guarantee a correct solution even for trained inputs, because you may miss the actual optimal value. Now let us see the testing algorithm. So the initial weights are taken from the training algorithm. So these are the final weights obtained during training. So you apply the final weights to the network as initial weights. And for each vector X to be classified, you perform steps 2 to 4. Set activations of the input units to X. Then you calculate the net input to the output unit, that is yin. This is equal to B plus summation I is equal to 1 to n xi wi. And you apply the activation function over the net input, that is 1 if net input is greater than equal to 0 and is minus 1 if net input is less than 0. In Adeline, you mostly use the bipolar function, and that is why you have y as 1 and minus 1. Then suppose, see, this Adeline is only for one neuron output, right? So only for binary classification. Suppose you want to do multi-class classification, right? Or suppose Adeline is not giving you very accurate results. Then you can choose multiple Adelines, right? You can have multi-layer adaptive linear element, that is multiple Adelines, and you can combine their results on the basis of some technique, say majority voting. So Madeline, applying this technique, when this technique was applied for the first time, that network was known as Madeline. So this was the first neural network which was actually applied in a real world problem of filtering noise in the telephone lines. So whatever you can see on the screen, the different triangular nodes that you see, they are actually the different Adelines, right? And then their results are combined in the final output node. So for terminology purpose, the intermediate node that you can see, which is having multiple Adelines, this will be called as the Adeline layer, and the final output layer where you are actually getting the output will be called as the Madeline layer. So the multiple adaptive linear neuron Madeline model consists of many Adelines in parallel with a single output unit whose value is based on certain selection rule. So it may use majority vote rule, right? So your multiple Adelines are giving some value, and then also, say you are using 5 Adelines, 3 are classifying an instance as 1 and 2 are classifying it as 0. Then on the basis of majority voting, you can assign the class 1 to such an instance. So this is the majority voting rule. So on using this rule, the output would have an answer that is either true or false, 1 or 0, right? So the weights that are connected from the headline layer to the midline layer, they are fixed, right? So if you, they are fixed positive and possess equal value. So if you see this architecture on the screen, the interconnections between the intermediate layer that is called the headline layer and the final output layer that is called the midline layer. So all these interconnections, they have equal weights. Okay. However, the weights between the input layer and the headline layer, they are adjusted during the training process. So the headline and midline layer neurons, they have a bias of excitation 1 connected to them. So the training process for a midline system is similar to that of an headline system, with the difference that here you have one additional layer of the headlines. So this is the architecture of the midline. So your n number of inputs are applied on the input layer having n number of neurons. Then these neurons are interconnected to the headline layer, which is also the hidden layer, having m number of neurons, Z1, Z2, Z3 and so on up till Zm. Now these weights, W11, W12, W13 and so on, these weights, they are adjusted during the training process, right? Now the interconnections that exist between the intermediate hidden layer, that is your headline layer, to the final output layer, Y, that is your midline layer, these weights, that is V1, V2, V3 and so on up till Vn, these weights are equal and they are not adjusted during the training process. They are all equal and having some any fixed value. Let us see the midline training algorithm. So the training is quite similar to that of headline, with the only difference that here we have one additional layer and one additional set of weights. So in this training algorithm, only the weights between the hidden layer and the input layer, they are adjusted, and the weights for the output units, they are fixed, right? So V1, V2, V3 and so on up till Vm, they are fixed and they have equal value. Here we have taken the value to be 0.5, that is 1/2. You can take any other value depending on the problem. So the bias again we have taken as 0.5 or 1/2, and the activation for the headline or the hidden layer and the midline units is given by fx is equal to 1 if x is greater than equal to 0 and -1 if x is less than 0. So let us see the algorithm. So first of all, we initialize the weights. The weights entering the output unit are set as above, and set initial random values for headline weights. So set some initial learning rate alpha. So learning rate you can take any value. Mostly people take 0.1 or 0.2, and for the V1, V2 and V3 for the example sake here we have taken as 0.5, and other weights like W1, W2, W3 you can take any random value for the first step. Then you perform steps 2 to 3 till stopping condition becomes true. Then you perform steps 3 to 7 for each bipolar training pair indicated by S:(T). So the input layer, at the input layer, you apply the input vector with the identity activation function, that is xi is equal to si. Then you calculate the net input to each hidden headline unit, that is Zinj is equal to bj plus summation I is equal to 1 to n, xi wij, j is equal to 1 to m. Right? J is 1 to m because we have m number of headlines. So n is the number of input neuron and m is the number of headline neurons. Then you calculate the output for each hidden unit. So Zj is equal to f of Zinj. That means you are simply applying the activation function over the net input at the align layer. Then you find the output of the net, that is yin is equal to b naught plus summation j is equal to 1 to m zj bj. So that means this final output at the align layer zj, this you are applying as input to the output Medline layer. Then final output you calculate by applying the activation function over this net input yin j. Then you calculate the error and update the weights. If t is equal to y, that means no error, then no weight updation is required, right? W new is equal to W old and B new is equal to B old. Otherwise, if there is an error, that is t is not equal to y and t is equal to +1, then you update the weights on zj where net input is closest to 0, right? So wij new is equal to wij old plus alpha 1 minus zinj xi. So here you have just fed the value of t. So since value of t is +1, we have simply replaced t in the above equation as 1. Similarly, bj new is equal to bj old plus alpha 1 minus zinj. Now, if t is not equal to y and t is -1, that is the target value is -1, then you update the weights on unit zk whose net input is positive. You simply replace t by -1. So wik new is equal to wik old plus alpha -1 minus zink xi, and bk new is equal to bk old plus alpha -1 minus zink. Then you test for the stopping condition. If there is no weight change or weight reaches a satisfactory level, or if a specified maximum number of iterations of weight updation have been performed, then you stop, else you continue. Okay, so that will be all for today. If you have any questions, you can ask. Okay, so no questions. Thank you all of you for your time. We will meet tomorrow again at 4 p.m. Thank you. See you again tomorrow.
Thank you.